So today I will also do some more problems. Okay, let me first state problem. Let y inside affine space, affine n space an uh, be an affine variety. And affine variety of dimension r. Also let h inside an be a hypersurface. It means that dimension of h, this is exactly n minus 1. Okay. And suppose y intersection h, this is non-empty, and y is not contained in h, means h does not entirely contain y. Okay. Then show that every irreducible component of y intersection h has dimension r minus 1. So this is a problem from Hartshorne actually. Okay. Now solution. Now in our last tutorial we have already seen that this dimension of y is equals to dimension of the coordinate ring ay. Now here it is given that dimension of y is equals to r. Okay. Now also in the last tutorial we have seen that the ideal of hypersurface, this is actually generated by a single non-constant polynomial. Okay. F is a non-constant polynomial. Constant polynomial. We can assume if we assume that h, this hypersurface, is irreducible, then means this f we can say that this is a irreducible polynomial. Anyway, now consider ay equals to this k x1 up to xn, we know, modulo the ideal of y. Now because okay, it is affine variety, so we are assuming that this is irreducible. Okay. Also we can assume that hypersurface is also irreducible. So this Iy is a prime ideal. We have already seen that. Now consider this map kx1 up to xn to the quotient map to ay. Now f is a polynomial inside this kx1 up to xn, this polynomial ring. So say f bar is the image in ay. Okay. Now we want to apply this Krull's principal ideal theorem. So for that we need a Noetherian ring, and we need an element inside the Noetherian ring which is neither a zero divisor nor a unit. Then we can say that the minimal prime ideal containing that element is of height 1. Okay, we will use that. So what Noetherian ring we are taking? We are taking this ay, this coordinate ring of y. Okay, and the element we will take will be the element we are taking is f bar. Now for that, first we have to show these things. First claim, this f bar is not a zero divisor. Okay. Now suppose f bar g bar, this is equals to 0 in ay. Okay. So this implies that f times g, this is inside iy. Now this implies that because iy is a prime ideal, so it says that f belongs to iy or g belongs to iy. Now we already know that okay, okay, say f belongs to iy, this will imply that y, which is equals to v of I of y, this will be inside v of f, right, and v of f is nothing but h. So f belongs to iy implies that y is inside h, but by our hypothesis we already assume that this y is not contained in h. So this is a contradiction. So this will imply that y is not inside iy, f is not inside iy. So this will say that g is inside iy. So this says that f is not a zero divisor. Now next claim is f bar, sorry, f is not a zero divisor, not f bar is not a zero divisor. Okay. Now the next okay, now the next claim is f is not a unit. Now suppose f bar is a unit in ay, then this implies that this ideal generated by this f bar, this is the whole ring ay. Now this implies that the ideal generated by f plus iy, this is equals to this k x1 up to xn, this polynomial ring. So this implies that v of f v of the ideal generated by f plus iy, this is equals to phi. Okay. Now y intersection h, now y is nothing but v of I of y, and intersection V of f, H is V of f. So, this is equals to V of the ideal generated by f plus I y. So, if this f bar is a unit, then it follows that this is equals to phi, right, but this is a contradiction also, a contradiction, because by our assumption, by in our hypothesis we assume that y intersection h is non-empty. So, y intersection h equals to phi, this is a contradiction. Okay. Then this implies that f bar is not a unit in ay. Okay. So, ay is a Noetherian ring and f bar is a element in ay, which is neither a zero divisor nor a unit. So, we can apply the Krull's principal ideal theorem, right. So, Krull's principal ideal theorem says that, so Krull's principal ideal theorem says that any minimal prime ideal containing f bar has height 1. Okay. Now, y intersection h is this is v of I of y intersection v of f, this is equals to v of the ideal generated by f plus I y. We have already seen this. Now, then observe that any irreducible component of y intersection h correspond to a minimal prime ideal say q in this polynomial ring k x1 up to xn containing f and iy, right, and also which also in turn correspond to minimal prime ideal q bar, which is nothing but q modulo iy of ay containing f bar, right. Now, so the dimension of the irreducible component corresponding to this q, so we can write it as vq, dimension of vq. This is equals to dimension of aq, sorry, not aq, but dimension of a of vq, means coordinate ring. Now, this is nothing but dimension of k x1 up to xn modulo I of VQ. Now Q is a prime ideal, so this will be equals to dimension of kx1 up to xn modulo Q, right. Now this is same as dimension of AY mod Q bar. So again a result from dimension theory states that this is equals to dimension of AY minus height of this Q bar. Now dimension of AY is equals to dimension of Y, which is R, we have already seen, and height of Q bar, this is height 1 by this Krull's principal ideal theorem. So this is equals to 1. So this is what we wanted to show. So okay. Next I will introduce the concept of cone of a I will introduce cone of a projective variety. Okay. I will not go into details, but I will just introduce and I will apply this the notion of cone of a projective variety. Okay. Now consider this map, this a n plus 1 minus this this point 0 0 0 0 0 to p n, this map theta, where each affine coordinate a naught up to a n, this goes to the corresponding projective coordinate a naught a n. Okay. Now suppose y is a closed subset in P n, then we define cone of y as this theta inverse y union this point 0 0 0 0, this point. This is called cone of y, cone of a projective variety, and projective variety, or you can say means algebraic subset in Pn, you can say. Now it has some properties. I will state these things, I will not prove these things. Okay. Cy is an affine algebraic set, in an plus 1, and its ideal is Iy, where Iy is the homogeneous ideal, corresponding to y. Okay. The second is Cy is irreducible if and only if y is irreducible. And third is dimension of Cy, this is equals to dimension of y plus 1. So these are some properties related to this cone of a projective variety, or projective means say any algebraic subset in Pn. Now here in the first problem, notice that here we have assumed that an affine variety, when we have a hypersurface in An, and if we have a affine variety y inside An, then we assume that that y intersection h is non-empty. But yeah, in affine case it is not may not be true that a variety of dimension at least 1 inside an it may not intersect with a hypersurface inside an, but inside Pn this is always the case, means every variety of dimension at least 1 it will always intersect with a hypersurface inside Pn. So okay, that's what we are going to prove. So this is also a problem from Hartshorne. Let y inside Pn be a variety also assume that this is irreducible of dimension, say at least dimension at least 1, okay, and let H inside Pn be a hypersurface. This means that dimension of H, again this is equals to n minus 1, this is a hypersurface. Also you can assume that this is also irreducible. Then y intersection H, this is always non-empty. Okay. Now proof, this is a application of this cone of a projective variety and also application of the previous problem, means actually it is the application of Krull's principal ideal theorem. Now consider Cy intersection H, consider this. Now Cy intersection H, this is equals to Cy intersection Ch, right, and this is always non-empty. Why? Because this point 0 0 0 0, this is always inside this is inside Cy, this is also inside Ch also, or say okay. Now H is a hypersurface. In the last tutorial we have seen that if H is a hypersurface inside An, then it is zero set of a it is zero set of a single irreducible non-constant polynomial. Okay. So in case of this a hypersurface in Pn, we can show that this is equals to, this hypersurface is nothing but zero set of a homogeneous polynomial where f inside k x naught up to xn is a non-constant homogeneous polynomial. Because we have we have assumed that the hypersurface is irreducible, so we can say that irreducible also, irreducible polynomial. Okay. So this is the case. Now we already know that Cy intersection H is an affine algebraic set, affine algebraic set in An plus 1, right. Now CH is a hypersurface. This is CH is a hypersurface. Why? Is a hypersurface surface in AN plus 1. Why? Because dimension of CH, this is equals to dimension of H plus 1. We just stated the properties of cone. So, dimension of H plus 1. Now, dimension of H is nothing but n minus 1 and plus 1. So, this is equals to n. So, CH is inside AN plus 1. So, this is a affine algebraic set. So, it has dimension n minus 1, right, and also H is irreducible. So, CH will be also irreducible. So, that CH is a hypersurface in AN plus 1. Okay. So, CH is a hypersurface in AN plus 1. Now, CY intersection CH, this intersects because 0 0 0 0 that point is here. So, we can apply the previous problem. So, this says that each irreducible component of this CY intersection CH, which is equals to CY intersection H, has dimension dimension of CY minus 1. So, dimension of CY minus 1 means this is equals to dimension of y plus 1 minus 1. So, this is equals to dimension y. Now, dimension of y, we assume that this is at least 1. So, this is greater or equals to 1. So, it says that this dimension of each irreducible component of CY intersection H is at least 1. Now, we have this map, right, this AN plus 1 to PN, AN plus 1 minus this minus this 0 0 0 0 this point to Pn, we have this map theta, right. So, it means that, and Cy is the Cy intersection H, this is nothing but y intersect theta inverse y intersection H union this 0 0 0 0 this point, right. So, now this Cy intersection H, this has dimension at least 1. So, this implies that y intersection H, this cannot be empty, because if y intersection is empty, so Cy intersection H will be only the singleton point 0 0 0 0 0 this point. So, then its dimension will be 0 dimension. So, but the case here is that dimension of each irreducible component of y intersection H of C of y intersection H is at least 1. So, this says that y intersection H is non-empty. So, this is a beautiful application of the concept of this cone of a projective variety and application of Krull's principal ideal theorem, whatever means yeah. Okay, let me stop here, we will continue in the next class.